It works on my machine, right? I mean, if you've spent any time at all in software development, you've absolutely heard this classic excuse, or let's be honest, probably used it yourself. It's basically a developer rite of passage at this point. But jokes aside, that one phrase perfectly captures one of the most hair-pulling universal headaches in tech: conflicting software environments. You know the drill. Your code runs flawlessly on your laptop, but the second a colleague tries to run it, or even worse, you try to deploy it to production, the screen just lights up with error messages. And why? Well, because dependencies, configs, and operating system versions just vary wildly from one machine to the next.
Welcome to This Explainer. Today, we're diving into a massive shift in how software is actually built and delivered. We're tracking the architectural evolution from rigid, clunky monoliths to agile, container-based microservices. And this isn't just some minor technical upgrade. We're talking about a fundamental rethinking of how digital products come to life. It's about empowering teams to ship faster, scale smarter, and finally put a permanent end to that whole "it works on my machine" syndrome.
Here's our roadmap for today. First, we'll tackle the monolith problem. Then, we'll get into the container revolution, followed by microservices and design patterns. And finally, we'll wrap up with the automated assembly line.
All right, let's jump straight into part one, the monolith problem.
To really understand why this revolution had to happen, we have to look at the stark structural differences here. In a traditional monolithic setup, literally everything, your user interface, the business logic, the data access, it's all tightly coupled into this one massive block, sharing a single database. Now sure, that's super simple when you're just starting out, but as an application scales, it becomes a massive bottleneck. On the flip side, a microservices architecture completely breaks the application apart. It isolates specific functionalities and data into independent, self-contained units, or services. Each one handles a distinct business function and usually maintains its very own data store.
And guys, the stakes of choosing the right architecture are incredibly high. Think about scalability. With a monolith, if just one single feature gets hit with heavy traffic, you are forced to scale the entire application. It's a huge waste of resources. But with microservices, you surgically scale only the specific service that actually needs it. Then there's risk management. In a monolith, changing one line of code can cascade and take down the entire system. Microservices isolate that blast radius. In fact, research shows that doing microservices right can slash development cycle times by up to 75%. That is literally the difference between dragging along a sluggish legacy system and shipping highly competitive modern software.
Which brings us to part two, the container revolution. So, to actually solve those monolithic headaches and execute microservices effectively, we had to totally rethink how we package code. Enter Docker. The best way to think about Docker is to picture a standardized physical shipping container, but, for your code. Just like physical containers completely revolutionized global trade by standardizing how goods move on ships, trucks, and trains, Docker ensures your application runs the exact same way everywhere. It packages the app, its runtime, system tools, and libraries into one lightweight, self-contained unit. It is the ultimate guarantee that if it works on your machine, it will absolutely work on your colleague's machine and on the production server. Now you might be wondering, why not just use virtual machines? Well, virtual machines create full system abstractions. They're running an entire, heavy operating system for every single application. They are super resource hungry, just eating up CPU, memory, and storage. Containers, though, are a fundamentally different beast. They actually share the host system's OS kernel while isolating the individual processes. Because they aren't dragging around the dead weight of a full OS, they're incredibly fast, super lightweight, and highly portable. Let's move on to part three, microservices and design patterns, specifically drawing on some fascinating insights from Google research.
Now that we've got the magic of containers, how do we actually organize them? Researchers at Google point out something I find really fascinating. Back in the 80s and 90s, object-oriented programming totally transformed software by popularizing modular components. Fast forward to today, and containers are sparking a very similar revolution. Think of containers as the new fundamental objects in modern distributed systems. When we start thinking in terms of containers, we can abstract away all those low-level code details and focus on higher-level design patterns. And that simplifies development and makes our systems vastly more reliable.
Let's look at how this builds into practical patterns, starting with the sidecar pattern. This is a single-node setup where you have closely cooperating containers sitting on one host machine. Imagine you have a main container, like a web server, and it's paired up with a secondary sidecar container, like a log saver, and they share the same local disk file system. The web server just does what it does best, serving content as fast as possible. Meanwhile, the sidecar is scavenging spare CPU cycles to save logs to a cluster. By separating them, different teams can build them. Plus, if the log saver crashes, your web server doesn't go down with it. It's brilliant.
Next up is the ambassador pattern, which essentially acts as a proxy. Let's say you have a main application that needs to talk to a complex distributed cluster of memcache nodes. Instead of hard-coding all that messy routing logic directly into your app, you just pair it with an ambassador container. Your application fires off a request to what it assumes is a single server on its local host. But the ambassador container intercepts that request and shards it across the actual distributed cluster behind the scenes. It completely simplifies the programmer's life.
Finally, we have the adapter pattern. So while the ambassador presents a simplified view of the outside world to your application, the adapter presents a simplified, homogenized view of your application to the outside world. A great example is centralized monitoring. You've got legacy apps and new microservices, and they're all spitting out metrics in completely different formats. An adapter container grabs those heterogeneous outputs and standardizes them. That way, your centralized monitoring system can interact with everything uniformly, and you don't have to touch a single line of the original application's code.
All right, that brings us to our final section, the automated assembly line.
So we got our architecture nicely containerized into these smart patterns, but how do we actually deliver it reliably? Well, you need an unstoppable, automated factory assembly line, and that is where Jenkins comes in. Jenkins acts as this tireless, automated worker for continuous integration and continuous delivery, or CI/CD. When you pair Jenkins with Docker, it is truly a match made in heaven. Jenkins orchestrates Docker to guarantee that your environments stay absolutely 100% consistent, from the exact moment a developer writes code on their laptop right through to the final production deployment.
By using what's called a declarative pipeline in Jenkins, we can map out a perfectly automated workflow. It goes like this. First, checkout. Jenkins pulls your latest code straight from the repository. Second, build. It reads your instructions and spins up a fresh Docker image. Third, test. This is crucial. It fires up an isolated container from that exact image to run automated tests, which ensures you have a perfectly clean environment every single time. And fourth, push. If all those tests pass with flying colors, Jenkins securely pushes that tagged, ready-to-deploy image directly into a Docker registry.
And the best part is, you can totally supercharge this pipeline with a few best practices. By optimizing Docker layer caching, you're only rebuilding the exact parts of the code that actually changed, which saves a massive amount of time. Jenkins can also run multiple containerized tests in parallel, slashing your testing phase. You can even shift left on security by baking image scanning right into the pipeline, catching pesky vulnerabilities before they ever sniff production. And if you use webhook triggers, the very second a developer pushes code, this entire automated assembly line springs into action instantly.
We have definitely covered a lot of ground today. We've gone from breaking out of those restrictive monolithic constraints to packaging our code in Docker, organizing everything via microservice patterns, and finally automating the whole shebang with Jenkins. So as you look at the sheer demands being placed on your own modern software systems today, I want you to ask yourself one final question. Is your architecture truly ready to ship the future?